This lecture is on bivariate correlational research. So after hearing this lecture, you should understand how to interpret a scatter plot as well as a correlation coefficient, understand how to interpret a bar graph by computing the difference between two means, be able to interrogate the construct of validity of an association claim, asking whether the measurement of each variable was reliable and valid, be able to interrogate the statistical validity of an association claim, including understanding outliers, effect size, restricted range, curvilinear patterns, and statistical significance. Be able to interrogate the external validity of an association claim by asking to whom the association can generalize, and know and understand three rules for causation, which are covariance, temporal precedence, and internal validity. So by bivariate correlational research, we're talking about associations that involve exactly two variables. Often the first variable is thought of as a predictor, and the second is thought of as an outcome. The association between these two variables, a predictor and an outcome, can be summarized statistically using the Pearson correlation coefficient. This is a single number that provides information about the direction and strength of the association between the two variables. A correlation coefficient can range from -1 to +1. 1.0 means that the two variables are perfectly correlated in a positive direction. 0 means that the two variables are not correlated. And -1 means that the two variables are perfectly correlated in a negative direction. And so in the scatter plots above, we see +1, 0, and -1. In everyday life, perfect correlations are very rare, of course. It's important to know that a correlation of 1 and -1 are equally as strong. It's just the direction is different. Similarly, a correlation of 0.5 and -0.5 are similarly strong in magnitude. Those would refer to an equal strength of association. It's just the direction of that association is different. Okay, and so here's 4 different scatter plots. So a scatter plot is where your data points are graphed along an x and a y axis. The x-axis is typically the predictor variable. The y-axis is typically the outcome variable. And each point represents a person usually. So in social sciences or in psychology, each point would represent a person, and each person has 2 scores. They have a score on the predictor variable, or they have a score on the outcome variable. So what a scatter plot allows us to do is look at the strength of the association between two variables. So in this top left panel, we've got a strong positive association. I just put in a number 0.75 as one that would represent a strong positive correlation. I don't necessarily know that that's the correlation here. It's an estimate. Here we see a scatter plot. This would represent what a number like -0.2 would reflect, so a weak negative trend or a weak negative correlation. Correlation of 0 in this lower right panel, so no association between the two variables, and this is what a perfect negative correlation would look like. So a scatter plot is a way to assess the strength of the relationship between two variables graphically, pictorially. Okay. So what you see here on the left is a scatter plot of data in which one variable, marital satisfaction, is quantitative, and the other variable, which is where the person met his or her spouse, either online or offline, is a categorical variable. Remember that with categorical variables, the values are categories. So it's possible to calculate a correlation between these two variables, and in this case, the correlation is 0.06, which is a small correlation. It's much more common to plot the results of an association between a quantitative variable and a categorical variable in a bar graph, which you see on the right. In a bar graph, each individual is not represented by a data point, but instead, with a bar graph, what is plotted here is the group mean, aka average, for marital satisfaction for the two different categories. So we can see that the average marital satisfaction among spouses that met online is approximately 5.5, but for those that met offline, it's about just lower than that, 5.4. So rather than plotting each data point, we just plot the group mean. So the online mean is slightly higher than the offline mean, and so that corresponds to a weak association between the two variables. So one takeaway is that even though we plot the association between a quantitative variable and a categorical variable, typically using a bar graph, it still represents association. It's still representing a relationship between these two variables by plotting the mean. And although it's possible to calculate an R, a Pearson correlation, when at least one of the variables is categorical, it's more common to use a statistic called a Ttest, which tests the difference between two group averages. And specifically, one would conduct an independent samples Ttest to look to see whether there is a mean difference between one group versus another, whether marital satisfaction differs, but depending on whether you meet your spouse online versus offline. Okay, so what actually makes a study correlational? The answer is that you have two measured variables. It's not the type of statistics used. So in other words, you can have a correlational study and look at the relationship or the association and analyze that relationship using a Ttest. You don't need to actually calculate a correlation. You can, of course, also calculate a correlation, but it's not the type of statistic that is used that determines whether you have a correlational study. What makes it a correlational study is measuring the two variables versus, say, manipulating one of the variables as in an experimental design. All right, so let's review some of the ways in which we can interrogate association claims. There are four, and we're going to interrogate the construct validity, the statistical validity, the internal validity, and the external validity. Okay, and so these are the questions that we're going to ask in interrogating each of those four types of validity. So let's start with construct validity. When interrogating the construct validity in correlational research, what we're really doing is asking about the construct validity of each variable. So how well was each of the variables measured? Does the measure have good reliability? Is the measure measuring what it's intended to measure? What is the evidence for its face validity, its concurrent validity, for its discriminant validity, and for its convergent validity? So essentially, we just need to do that for both measures involved. Statistical validity can be interrogated, and we need to consider 5 different aspects of statistical validity, so I'll go over each one of these. So the first is to consider effect size. When we're interrogating statistical validity, we need to consider effect size. The idea here is that effect size is the strength of association. It's the size of that correlation coefficient. Some associations are stronger than others, and the effect size describes that strength of association. So if we look at our two figures here, we've got panel A and then we've got panel B on the left and panel A on the right. In both of these scatter plots, we've got a positive association between our two variables, x and y. Why is there a positive association? Because the dots are going in a positive trend such that positive numbers on x are associated with positive numbers on y, or high, I should say higher numbers on X are associated with higher numbers on Y, and lower numbers on X are associated with lower numbers on Y. So highs go with highs, lows go with lows, middles go with middles. It's a definition of a positive association. That's the case in both panel B as well as panel A. But we can see that there's a stronger association or a stronger effect in panel B than panel A. So panel B depicts a stronger effect size. And we can use Cohen's guidelines for evaluating the strength of association based on the size of the correlation coefficient, with 0.1 indicating a small or weak correlation, 0.3 indicating a medium or moderate correlation, and 0.5 or higher indicating a large or strong correlation. Okay, so if you land somewhere in between 0.1 and 0.3, you'd say, well, that's small to medium. If you land somewhere between 0.3 and 0.5, you might say, well, that's medium to large. But if you're 0.5 or over, that represents a large or strong association between those two variables. And what we can say is that when we have a larger effect size, we can make more accurate predictions. Okay, so a strong effect size enables more accurate predictions. The more strongly correlated two variables are, the more accurate our predictions can be. So both of these scatter plots also depict positive correlations. But you can see that in scatter plot A, a stronger relationship is depicted. So that means we can make more accurate predictions from the data that are in panel A. Okay, and what's graphed here is height of research participants at age 2 and at age 18. So what this stronger association and this larger effect tells us is that we are more accurate in making a prediction about how tall somebody will be at age 18 from their height when they're 2 years old, based on this pattern of data, than we are at trying to make a prediction about how tall somebody will be based on their mother's height. Okay, so in this panel, the effect is smaller, the correlation is weaker, and therefore we are less accurate in our predictions. So stronger effect, more accurate prediction. Generally speaking, a larger effect size is considered more important than a smaller one. However, there are some exceptions. Depending on the situation, even a small effect size can be important. So for example, there's been medical research on heart attacks and taking aspirin. And this research has found a very small correlation only negative 0.03, between taking aspirin, or the extent of aspirin taken, and heart attacks. So what we see there, the more aspirin one takes, the fewer heart attacks. But that'd be considered a very weak correlation based on Cohen's guidelines. However, consider this. In this particular study, there was 22,000 participants, 11,000 in an aspirin group and 11,000 in a placebo group. And they found that there was 85 fewer heart attacks among those that took aspirin. So 85 is a significant number. It's an important number when we're talking about lives saved. So when we're talking about an important or critical outcome, even a small effect size can be considered important. But generally speaking, the larger the effect, the more important it's considered to be. Okay, some exceptions to that rule, though. All right, so let's talk about statistical significance. Statistical significance refers to the conclusion that researchers make regarding how probable it is that they would get a correlation of a particular size just by chance assuming that there's not a correlation in the real world. Okay, so it's a somewhat backwards way of making an inference. Okay, so the logic goes like this. Researchers collect data from a sample, and they do so to make an inference about the population. And the idea is that if there's an association between two variables in the population, usually there is in the sample as well. Similarly, if there's no association between two variables in a population, usually there's no association in the sample either. However, sometimes, even if there isn't an association in the population, simply by random chance, there may be an association in the sample. And that's due to something called sampling error. That is, because we're dealing with a smaller set, a sample of the population, the statistics that we calculate in our sample can sometimes be in error. Okay, so even though there isn't, we could say, even though there isn't an association in the population, sometimes we could find an association in our sample, and that could merely be due to sampling error. So calculating statistical significance helps researchers evaluate the probability that the result could come from a population in which the association in the population is actually zero. So in some ways, we're trying to rule out that the true correlation in the population is zero. Okay, so then what does that mean then? What would it mean to get a statistically significant result? A statistically significant result refers to the probability that the association in the sample came from a population with an association that is also zero. Okay, that's the null hypothesis. The null hypothesis is that the true population correlation is zero. So what we're doing is we're coming up with a probability estimate. Okay, and we're saying that if the probability is small, specifically, if the probability, or P, is less than 5%, what we're saying is that there's a less than 5% chance of observing a correlation as big as we calculated in our sample simply due to random sampling error, assuming that the null hypothesis is true. So if we observe in our sample that we have a large correlation, that might give us reason to reject the null hypothesis, because we would say that there's a less than 5% chance we could get a large correlation if the true population correlation is zero. Therefore, the true population correlation can't be zero. We expected something different. Well, so what would a non-significant result mean? This just means that based on the data we have from our sample, we can't rule out that the true correlation in the population is zero. Okay, we can't rule it out. So if we get some p-value, some probability that is relatively high, which by convention would be greater than 5%, we're saying that there's a greater than 5% probability of sampling a correlation this high, even if the true population correlation is zero. Okay, so therefore we can't rule it out. We can't rule out that the correlation is zero. It doesn't mean that the true correlation is zero. It just means we don't have sufficient evidence in our data to say that it isn't. All right. Now, there's a relationship between effect size, which is the size of the correlation, sample size, and significance. So the stronger a correlation, the larger the effect, and the more likely it is that the correlation will be statistically significant. So we need to examine the p-value, okay, that value which tells us the probability of getting a correlation of a particular size, assuming that the null hypothesis is true, which is that the population correlation is zero. So we need to look at that p-value but that p-value is dependent on both the effect size and the sample size. A very small effect might be statistically significant for a large sample, but not for a small sample. Okay. So what we do is we have to use some way to determine whether our correlation is statistically significant. So here's one example. So before computers and software, statisticians had to develop lookup tables. So what we have here is a table of critical values. And this actually illustrates very nicely the relationship between effect size, sample size, and significant. So the smaller the sample size, which is reflected in degrees of freedom. Okay, in calculating a correlation coefficient, degrees of freedom is calculated as sample size minus 2. So basically these numbers reflect sample size. So degrees of freedom 1 would be a sample size of 3, degrees of freedom 2, sample size of 4, etc. So you can see here that the lower the degrees of freedom, the lower the sample size. The higher the degrees of freedom, the higher the sample size. So we can see that the smaller the sample size, so lower degrees of freedom, the higher the effect needs to be. So we need larger correlations in order to be considered statistically significant. Let's take our conventional alpha level of 0.05. If we had a sample that was only 6 people, so degrees of freedom 4, we would need to calculate a correlation of 0.811 between those two variables to determine that that's a statistically significant correlation. However, the higher the sample size, the smaller the effect needs to be. So at our 0.05 level, let's just go all the way down to our last row in the table. If we've got a sample that has 22 people in it, so degrees of freedom 20, we would only need a correlation of 0.423. Okay, so you can see the difference in sample size. In order to say that a study of 6 people, that there's a statistically significant correlation, you need a correlation that is at least as big as 0.811, positive or negative. But with 22 people, you only need a correlation of 0.423, positive or negative, to say that that's statistically significant. And it has to do with random sampling error. When there's only 6 people in a study, it's possible, just due to randomness and chance factors, that you could calculate a correlation that is larger just due to chance. So we need to see a larger correlation in a small sample in order to conclude that it is not due to chance factors. When you read journal articles, it's very common to see something called a correlation matrix. The correlation matrix will have study variables in both rows and in columns. And what you'll just do is to see the correlation between two variables is take a row and then go to the different columns. So what we're looking at here in row 1, this is the correlation between employees' perceptions that employees are treated equally in their company, and that correlates at 0.67 with their perceptions that employees are given equal access to opportunities in the company. So this is the correlation between variable 1 and variable 2. Okay? Correlation between variable 1 and variable 3, correlation between variable 1 and variable 4. Let's go over here. This is the correlation between variable 2 and variable 5, which is climate for innovation. Okay? So this is a correlation matrix, and this is a way to very succinctly share what all the bivariate correlations are between all the variables in a study. You can also see some descriptive statistics, so mean, standard deviation. There were 2 samples here, so we've got study 1 correlations are below the diagonal, study 1 correlations are above the diagonal, and then a note that all correlations are significant. Okay, so all correlations met the threshold for statistical significance, not just at the 0.05 level, but actually at the 0.01 level. Okay, so that's an example of presenting correlational research. Okay, other things to keep in mind when interrogating the statistical validity of a correlational claim is to consider whether there are any outliers in the data. So an outlier is an extreme score that lies far away from the rest of the scores. So we've got two different sets of scatter plots. All right. One set of scatter plots is a larger sample, and then the set of scatter plots on the right, we have a smaller sample. And you can just see that there's more dots in the larger samples and fewer dots in the smaller sample. The only difference between graph A and graph B for both a large and a small sample is the presence of an outlier. So on the left here, you can see that this outlier value, all we've done is take this data point and just make it an outlier. And then the same thing was done in the panel on the right. So this point right here was just made into an outlier. So what this is illustrating is the effect that an outlier can have on the correlation coefficient. The correlation for the top graph in the large sample is 0.37, and for the bottom graph it's 0.26. So you can see that just having this outlier variable that ends up generally being in the same trend. We've got a weak, kind of we can say a small to moderate positive trend here. That small to moderate positive trend is strengthened by the presence of an outlier. And that's also the case in the smaller sample. But what this illustrates is that an outlier value has the most influence when the sample is small. Okay, so in a small sample, that single outlier value has a more powerful or influential effect on the correlation coefficient, jumping from 0.51 to 0.49, versus in the larger sample, the correlation only jumps from 0.26 to 0.37. Now, one thing to know is that an outlier does not always strengthen the correlation. Here we have an outlier strengthening the correlation because the outlier is falling in the same general pattern. There's a positive pattern and that outlier is falling in that same pattern. But if the outlier is had a different value, it might severely weaken or reduce the correlation to zero. So an outlier does not always necessarily strengthen the correlation. It has to do with whether that correlation falls in the same pattern of data with the other data points. Another concept to keep in mind when considering statistical validity is the concept of restriction of range. So a restriction of range happens when there is not a full range of scores on one of the variables in an association study. And that can make the correlation appear smaller than it really is. So if you look at this graph, you'll see that the two variables are college grades and SAT score. And in this case, SAT score is conceptualized as the predictor and college grades are conceptualized as the outcome. That is, we're trying to predict GPA from SAT scores. So the data are from a very highly selective college that only admits students with high SAT scores. The plot of the correlation between college grades and SAT yields a positive relationship, but the relationship doesn't appear to be very strong. So now let's take a look at, this was the pattern of data that we're looking at. Now look at this bottom panel. Scores on the SAT can range from, I believe, 600 to 2400, but College S only admits students who score 1200 or higher. So this creates a restriction of range. We could extrapolate from that top scatter plot and see what the scatter plot would look like if the range was not restricted. In the top scatter plot, the correlation is 0.33. In the bottom scatter plot, where the range is not restricted, the correlation is 0.57. Okay, so when we include all the people that were not accepted into the college, but would have been accepted at, say, less selective colleges, you can see that there's a much stronger relationship. So, what can researchers do about restriction of range? Well, researchers can recruit more participants in a study to try to widen the range. In this case, rather than looking only at one selective college, you would want to look at a range of different colleges. There are also statistical techniques that allow for correction of restriction of range that are fairly complicated, but occasionally you might run into that if you read a research article. The researchers might make a statement that the correlations that they are presenting are corrected for restriction of range, and this is the phenomenon that they're referring to. Okay, another thing to consider is that a correlation is a number that describes the strength of linear association between two variables. But sometimes there's a relationship between variables that are non-linear. Here's a good example. In the graph, we've got a curvilinear association. The pattern of the data forms a curve. So we've got age in years on our x-axis, and we've got use of the healthcare system on the y-axis. And as you can see, it's very common to use a healthcare system when you're very, very young. So when you're first born, and during the early years of life, you got to go to many doctor's appointments, you get all your shots. In your 20s and your 40s, it's less common to use the healthcare system for a typical person. And then as you get older and you age and you have health complications, you use the healthcare system much more regularly. So what you can see is that there is a strong pattern here. There's this very strong U-shaped relationship between age and years and use of the healthcare system. However, if you were to calculate the correlation coefficient, you would calculate a correlation of 0.01, okay, which doesn't at all capture the strength of the data or the strength of the relationship. And this is because a correlation coefficient captures a pattern of linear, as in straight line, association. Okay, so it's not appropriate to use a correlation coefficient to reflect a curvilinear pattern of data. All right. Now it's worth asking whether we can interrogate the internal validity from a association study. Typically, it's not a priority to do this, to interrogate internal validity when making an association claim. Really, internal validity is really only a priority when we have a causal claim. But we still do want to consider internal validity because we want to be aware of the temptation to turn an association claim into a causal claim. We've heard the statement that correlation is not causation. Why is that? Well, the reason is that in order to make a causal claim, a study has to satisfy three criteria. The first is covariance. Okay? Covariance refers to the idea that there must be an association between a causal variable, which we'll call A, and the effects of that variable, B. Okay? So what an association study can show is this first criteria. It can show covariance. All right, but what about temporal precedence? Temporal precedence asks the question, does the method establish which variable came first in time? Is the study able to show us, or are we able to infer that variable A comes before variable B? Okay, because if it's the case that the study can't establish, or if we can't tell which variable comes first, we can't infer causation. Let's go back to one of the examples that we were talking about, which is SAT and college GPA. we could actually have an association study in which temporal precedence is satisfied. Why? Because you take the SAT first and you use that to get admitted to college, and then you take your college classes, and then you get grades, and then a GPA is calculated. So if we see a correlation between SAT and GPA, covariance is established, and temporal precedence is also established. Okay, but those are the questions that we're asking. Now, the third criterion is the internal validity question, and this is often known as the third variable problem. So we can say, is there a C variable that is associated with both A and B independently? And if there's a plausible third variable, we can't necessarily infer causation. So going back to our SAT and GPA example, there's likely several third variables that affect both SAT score as well as college GPA. And so some of the variables might be success in high school, so high school grades, the amount that one learns in high school, socioeconomic status, having parents that are college graduates, say parenting practices. So there's a number of third variables that affect academic accomplishment that would be reflected in both the SAT as well as college grades. So it's any study that would measure the association between SAT and GPA would run into those third variable problems, even if they had established the covariance and temporal precedence criteria. Okay. Now, it's interesting that when we come up with a third variable explanation for an association, we can ask whether there's a problem for internal validity. So what we have here in this example is in the textbook, but we've got a correlation between the well-being that people report and the percentage of substantive conversations. So in this example, it's the amount of conversations where you get and have like a deep conversation, like deep talk, talking about things that matter. Okay, so talking about having conversations of substance. And in the research, people found that there is a correlation between people's well-being and the percentage of conversations that they have with others that would be considered deep talks. So overall, there's a moderate positive correlation. But look at what happens when participants are separated into two subgroups based on education, as we have here in this left graph. So the green dots represent people that are more educated, and the blue dots represent people that are less educated. Note that the educated participants, the green dots, tend to score higher on both variables. So in general, they report higher well-being, and they report having more substantive conversations, deeper conversations. People that are lower education score lower on well-being and score lower on percentage of substantive conversations. That is, they report having fewer deep talks. So what we have here is a third variable problem. It's likely education that is responsible for the correlation that is observed between the entire sample of well-being and the extent of deep talk. Because what you can see when looking at the subgroups, there's zero correlation. If you just focus in on those green dots, zero correlation. Focus in on those blue dots, zero correlation. But when combined, we see that positive pattern. So there's a third variable problem. Here, which is also, we could say that there's a spurious association between those two variables. But let's look at the example and the scatter plot on the right. If you look at, we'll make our more educated people the orange dots here, and the less educated people the navy dots. And if you look at each of those subgroups separately, you see that there's still a positive association between deep talk and happiness. So if you only look at the orange, still a positive correlation. If you only look at the navy, still a positive correlation. So in this case, although level of education might be, it's possible, it still could be a third variable explanation for the results. Deep talk and happiness are nonetheless correlated within the two different education subgroups. And so in this case, we wouldn't say that there's necessarily an internal validity problem in this pattern of results, whereas there is here. Okay, one more concept I'd like to discuss is the concept of a moderating variable. So when the relationship between two variables changes, depending on the level of another variable, that other variable is called a moderator. So a moderator variable changes the relationship between a predictor and an outcome. Okay, a moderator variable changes the relationship between a predictor and an outcome. Let's do an example. This is in the text. I think is a good way to understand what a moderator is. So this study, they wanted to see if there was an association between the attendance at professional sports games and the success of the teams. And so they thought, yeah, the more successful the team, the greater the attendance. And so what they did is they studied this with Major League Baseball and Major League Baseball seasons. And what they determined is that the strength of the relationship between attendance at games and the success of the team was moderated by whether a city had high versus low residential mobility. Residential mobility just means that people are more likely to move in and out of the city, whereas low residential mobility means people are less likely to move in and out of the city. And so using data gathered over many seasons, researchers determined that in cities with high residential mobility, there's a positive correlation between team success and attendance. So what this indicates is something called a fair weather fan base. We're only going to be your fan if you're performing well. And that makes sense, really. If it's high residential mobility, you don't necessarily have the roots to the city. You're not a diehard and loyal fan. And so, people only go to the see the team play if the team's doing well, and they don't go if they're not. But look at Pittsburgh. Pittsburgh has low residential mobility. That is, there's not a lot of people leaving or moving to Pittsburgh. It's a relatively stable population. And you can see here that there is a non-significant relationship between success and attendance. So whether the team is doing well or not so well doesn't really have any relationship with the amount of attendance in any given season. So what we have here is residential mobility is a moderating variable that moderates the strength of the association between team success and game attendance. Here's a graphical view. Here each dot represents one of the seasons. Okay, and so for each team, this is the percentage of wins, and this is attendance. And so you can see this is with the Arizona Diamondbacks. So in this particular, these seasons, they won a majority of their games, higher attendance. And these seasons, they won few of their games, generally speaking, lower attendance. So we got a positive correlation in Arizona, but in Pittsburgh, there's a negative correlation, but it was a non-significant correlation. So we don't want to make too much of that. All right. So again, a moderating variable is one that changes or affects the strength of the association between two variables.